Okay, let's just dive right into this explainer and decode the notoriously complex Navier-Stokes equations. I know, they look intimidating, but these are actually the hidden rules governing practically everything around us, from the slow, sticky flow of honey on your toast to the chaotic, violent gusts of a thunderstorm. Whether you're a hardcore engineer or just someone who's super fascinated by the natural world, getting a grip on fluid dynamics means understanding the absolute, invisible forces shaping our reality. Let's get into it. Here's our roadmap for breaking down this massive mathematical puzzle today. We're going to start with the equation of everything, look at the anatomy of fluid motion, explore perfect order with laminar flow, hit the transition to chaos, and wrap up with taming the turbulence for real-world engineering. All right, section 1, the equation of everything and the continuum field approach. We're starting right at the foundational core of fluid mechanics. Now, believe it or not, this is essentially just an elegant formulation of Newton's second law of motion applied to a continuous fluid. Instead of driving ourselves crazy tracking individual bouncing molecules, we use a continuum mechanics approach. We frame fluid behaviors through big, macroscopic variables like density, velocity, and pressure. But to really understand this, we have to choose how we look at the fluid. Tracking billions of changing individual particles, that's called the Lagrangian way, is literally like trying to follow every single car on a jammed-up highway. It gives you a mathematically impossible system of equations. No thanks. So instead, we use what's called the Eulerian approach. Imagine we just set up a fixed toll booth in space and simply watch how properties like velocity and pressure change as the fluid flows past that one specific spot. Much easier, right? Because we're looking at fixed coordinates rather than tracking a moving object, calculating acceleration requires a really special mathematical tool. The material derivative. It captures two things simultaneously. First, the unsteadiness at one spot, kind of like a sudden gust of wind hitting a stationary sensor. And second, the spatial changes a fluid parcel experiences as it moves into a new area, like water suddenly speeding up as it forces its way through a narrow nozzle. Moving right along to section 2. Anatomy of fluid motion and momentum conservation. Let's see how all of this builds into the complete vector expression by breaking down this terrifying equation into totally manageable pieces. So the crucial takeaway here is that this isn't just abstract mass. It's a dynamic accounting ledger. On one side, you have the inertial forces, local and convective, acting as the source of all the dynamic complexity. And fighting against them, constantly battling for equilibrium, are the forces trying to push or drag the fluid. You've got the pressure gradient driving flow from high to low, viscous forces acting like internal friction, and body forces pulling on it, like gravity. Every single curve in a river is the direct physical result of these exact forces striving for balance. Okay, section 3, perfect order, laminar and exact solutions. You see, when flows are perfectly steady and symmetrical, those super complicated nonlinear convective terms, they just disappear entirely. And that allows us to find beautiful, exact mathematical solutions. In these highly orderly regimes, viscous forces act kind of like thick syrup to perfectly balance out pressure and shear. And the result? Incredible geometric shapes right in the real world. For instance, in a circular pipe, the fluid forms a perfect velocity parabola. The dead center moves the absolute fastest because it's avoiding the drag of the walls. Or, if fluid gets trapped between a stationary bottom plate and a moving top plate, you get this pure, straight-line shear profile. Momentum is just handed down layer by layer with zero pressure driving it. It's actually really elegant. But of course, we have to ask the big question. What on earth happens when the chaotic power of inertia eventually overwhelms the organizing, shock-absorbing power of viscosity? Because as the velocity ramps up, that perfect structural symmetry is absolutely destined to violently break down. Which brings us to section 4, transition to chaos, and the breakdown of order. We are now entering the wild territory, where small disturbances no longer just decay smoothly away. Instead, they amplify into chaotic, unpredictable motions. Welcome to the realm of turbulence. To figure out when this happens, we use the Reynolds number. This is basically the ultimate dividing line between order and chaos. Think of it as a mathematical gauge of stability that tells us exactly who is winning that physical tug of war we talked about. It takes the fluid's density, its velocity, and its length scale and simply divides them by the fluid's viscosity. And here is the magic number. In a standard pipe, when the Reynolds number hits a critical threshold of right around 2300, that's it. The fluid's inertia finally overwhelms the viscous dampening. The shock absorbers completely fail. Minor surface ripples suddenly amplify and literally shatter those symmetrical layers into a spiraling mess of chaos. It's an amazing contrast to see. A fluid acting like thick, predictable syrup fundamentally transforms into a wild river driven by rapid convective mixing. The orderly, neat diffusion of momentum is completely erased, replaced by these three-dimensional, violently unpredictable structures called eddies. This turbulence sets off what we call an energy cascade. It's like a cosmic relay race. Massive vortices break down into smaller and smaller eddies. Kinetic energy enters at the very largest scales and transfers downward with virtually zero energy lost. It keeps cascading until the eddies reach the microscopic level, the Kolmogorov scales, and that is where the energy is finally burned off by viscous friction. Because this gap between the massive scales and the microscopic scales is so huge, trying to simulate all of this on a computer requires absolutely enormous processing power. Which leads us to Section 5, taming the turbulence through RANs and modeling. Since directly computing every single microscopic eddy is practically impossible, engineers have had to cleverly hack the math to design real-world things like airplanes and massive pipelines. So to make these calculations feasible, we use something called Reynolds decomposition. This trick separates the chaotic, instantaneous flow into stable, predictable averages alongside the high-frequency fluctuations. Essentially, every fluid property gets split into a nice, smooth mean value and a chaotic prime value that's just jumping wildly up and down over time. However, doing this creates a massive mathematical headache. Averaging the equations produces a phantom variable known as the Reynolds stress tensor. It's not true molecular friction, rather it's an apparent macroscopic drag caused by those chaotic eddies. But here's the catch. Because we don't know the exact values of these fluctuating correlations, we end up with more mathematical unknowns than we have equations. This, my friends, is the infamous closure problem. Modern computational fluid dynamics, or CFD, uses a few distinct strategies to overcome this headache. Direct numerical simulation, or DNS, solves everything exactly, but the computing cost is literally astronomical. Large eddy simulation acts as a pretty good middle ground. Then there's RANs, the Reynolds averaged Navier Stokes approach. This simply models all turbulent scales using an artificial eddy viscosity. RANs is the cheapest, it's the most practical, and it remains the absolute industry standard for engineering today. Let's look at how this plays out in the real world. Imagine an engineer sizing a 500-meter industrial pipeline for heavy oil. By walking through these exact steps, finding the main velocity, figuring out the maximum centerline speed, calculating the required pressure drop, and finding the wall shear stress, they solve the problem. But crucially, in step 5, they verify their assumptions by computing that Reynolds number. If they calculate a number around 600, well, that's way below the 2300 threshold. The viscous dampening is stronger than the chaos, proving their laminar design is perfectly safe to build. Ultimately, what these wildly complex Navier-Stokes equations are describing is an epic, continuous cosmic struggle happening in literally every body of liquid and gas on the planet. It's an incredible, delicate balancing act of momentum, heavily governed by geometry, that's just constantly tipping between total symmetric order and infinite fractal chaos. I really hope this explainer sparked your curiosity today. The next time you stir cream into your morning coffee or watch the wind rip through the trees outside your window, I challenge you to look at the fluid motion all around you and ask yourself, if the simple flow of water in a pipe hides such immense mathematical complexity, what other hidden rules are governing the world right before your eyes?